So now that I've decomposed every data point into the fit plus the residual, I need to go on to do the statistics necessary to test whether the main effects have an effect or so on. But before I do that, I want to do a little bit of checking. In particular, let me just put an underline under all of this. The sum of all of the main effects and the interaction and the residuals should all be 0. So let me go ahead and check this to make sure that I've not made some kind of computational mistake. So I'm going to sum up the main effect for the temperature, and that comes out to be 0. And then I can just copy this sum formula. The main effect for pressure is 0. The two-way interactions are 0. The residual is 0. The y-hats won't sum to 0. But I've now basically checked my calculation at this point. I'm also going to want to compute here the deviation of each y observation from its mean, which is going to be helpful to me in computing the sum of squares total, which I'll get to in just a minute. So let me firstly compute the y deviations. So that's going to be equal to the value y minus the average of all of the y data and I better hit F4 here because I'm going to want to slide this down. So we can see, for example, that the very first observation of 39 is 11.36 units higher than the average. So now I can just go ahead and copy those down through the column. And these y deviations, if I've computed them correctly, also ought to sum to 0. So let me go ahead and check that by copying the sum formula over. Sure enough, it's 0. So now I've basically checked my fit, and I can compute the sums of squares that are going to go into my analysis of variance. I can compute these extremely easily. All I do is square each and every entry in the column and add it up, which I can do with the Excel formula sum square. So this is where the real simplification comes in terms of understanding this. I don't have to remember B's and N's and G's, and I don't have to compute averages of subgroups with this dot formula and so on. It's just very simple. All I've done is decompose each and every observation, and then the sums of squares are simply the sums of the corresponding columns. So the sum of squares for temperature comes out to be 23.51. The sum of squares for pressure, I can just copy this formula over, is 1034.84. The sum of squares for the interaction is 139.56. And finally, the sum of squares for the error is 924.4. And I computed this y deviation because the sum of those squared gives me the sum of squares total. So let me just copy the formula over one more time, and you can see that the sum of squares total is 2,122.31. All right, well, now that I have computed all of my sums of squares, I can start to load them into the analysis of variance table. So I just go into the analysis of variance table that I've set up here, and I just copy in, so I'll use an equal sign, the sum of squares for temperature. So I go up and grab temperature, then the sum of squares for pressure, then the sum of squares for the interaction, and finally the sum of squares for the error. And then the sum of squares total ought to be the sum of all of the other sums of squares. So I'm going to sum all of the other sums of squares, the sum of squared temperature through the sum of squares residuals or the sum of square error. and that gives me a sum of squares total, which is 2122.311, and that had better be the same as the sum of squares total that I computed by summing up the squared y deviations. And it is, and this gives me a check. Now basically, in order to determine if temperature or pressure or both or the interaction are significant, I'm going to be asking the question, are these sums of squares too big to have occurred just by chance if this factor has no effect? And I do this very, very similarly to how the analysis of variance table is set up in regression. I'm going to take my sums of squares. Each and every sum of squares has a degrees of freedom. I'm then going to compute the mean squares, which are just the sums of squares divided by the degrees of freedom. And then, using these mean squares, I can basically ask if the amount of fit obtained by each of these factors is too big to have occurred by chance if there really was no relationship. So the next thing I need to do is to put in the degrees of freedom. The degrees of freedom for any factor is the number of levels minus 1. So for example, for temperature there are 3 levels, and then I take 1 away from that and I get the number of degrees of freedom for temperature. Similarly for pressure, I would take the number of levels for pressure, subtract 1, and that would be the degrees of freedom for pressure. It just so happens in this particular case that pressure and temperature both have 3 levels, so the degrees of freedom for pressure is also 3 minus 1, which is 2. Now the degrees of freedom for the interaction is just the product of the degrees of freedom for each of the main effects for temperature and pressure. So it's going to be 2 times 2, which is 4. Now the degrees of freedom for the total sum of squares is exactly the same as it is in univariate statistics or for the total sum of squares for regression. Namely, it's the sample size, the number of observations minus 1. So I can compute that by using the function count and then selecting out the entire column of y's and then subtracting 1. So you can see that the degrees of freedom associated with the total is 44. Now the degrees of freedom for the error or the residuals is just the difference between the degrees of freedom for the total and the other degrees of freedom. So I can put in the formula here. It's equal to the 44 minus now the sum of the degrees of freedom for temperature, pressure, and the interaction. Okay, so now the next thing to do is to compute the mean square. So the mean square is always the sum of squares divided by the corresponding degrees of freedom. So for example, the degrees of freedom are 2 for temperature, so the mean square is half of the sum of squares. The sum of squares was 23.51. The mean square then is 11.76. Now I can just copy this formula down. All right, now I'm going to get into the statistics, so to speak. And what I'm going to do is compute for each of the main effect for temperature and pressure and for the interaction an F statistic, which is just the ratio of the corresponding mean square to the mean square error. So the basic idea here is that the mean square error represents how much mean square you get due to random noise. And what we're going to be asking here is the mean square due to one of these variables, like for example pressure, so big that it couldn't be just due to random noise? If it were due to random noise, then the ratio of the two mean squares ought to be about 1. So the next thing I do is compute each of the F statistics. I compute each F statistic as the mean square divided by the mean square error. And since I want to copy this formula down, I better hit F4 to make the reference to the mean square error a fixed reference that won't change. So I can see now that the the F statistic for temperature is 0.45. As I copy this F statistic down, I get that the F statistic for pressure is 20.15. For the interaction, it is 1.35. Okay, so just eyeballing this, it looks like the F statistic for pressure is pretty big at 20, and the others are pretty small. If I thought these ratios ought to come out about 1, if really nothing was going on. But it's very hard to interpret the F statistic, so what I really need to do now is to compute the p-value. Well, the F statistic is called the F statistic because it has an F distribution. And so my p-value is going to be an upper tail probability of being above the statistics value using an F statistic. Using an F distribution. So for example, the p-value for the temperature main effect is going to be 1 minus F dot dist Okay, it's 1 minus because I need the upper tail probability. I then put in the value of the F statistic. And now the F distribution requires 2 sets of degrees of freedom. One for the numerator, which is the 2, and then one for the denominator, which is the degrees of freedom that are associated with the sum of squares error, sum of squares residuals. Now I'm going to want to copy this formula down through the table, and I always want to reference the degrees of freedom for the sum of squares error. So I better hit F4. And then finally, like most of the distributions in Excel, I need to put in true for cumulative, or it just gives me the height of the density function, which is not something I typically want. So what you can see here is the p-value associated with the temperature is 0.636. And so we fail to reject, since this is bigger than any typical significance level that you might pick. So we fail to reject the null hypothesis that temperature has no effect. So what this says is there's no evidence in this data that temperature has an effect. Now I can copy that formula down for both the pressure and the interaction. And I guess I'll change the format here of the pressure. It comes out at 1 times 10 to the minus 6, which of course is a very small number. So let me just format the cell and turn this into a number. And so you can see that the p-value for the pressure is essentially 0, which indicates that there is strong statistical evidence that pressure does in fact affect this reaction. And then finally, the p-value for the interaction is about 26%, and this again shows that there's no evidence in this data that there's a nonlinearity that's not explained by the additive nature of the two factors. So in summary then, what we found here is that pressure affects the reaction, and we don't have any evidence that temperature affects the reaction or that there's any kind of a nonlinearity. So in summary, what I've done is greatly simplify the formulas associated with the two-way analysis of variance by simply thinking about decomposing each and every observation into a fit plus a residual. And in the case of two-way analysis of variance, the fit is based on the average of everything, then the main effect for temperature, which is simply the average of everything like me on temperature minus the grand mean. This represents the shift that this level of temperature, namely level 3 in the case that I'm highlighting, has on the response on average, the shift from the grand mean. So then I do the same thing for the main effect for pressure. It's just the average of everything like me on pressure minus the grand mean. The interaction then is the average of everything like me on both temperature and pressure minus the grand mean and minus the two main effects. This means that the predicted value for the model, the fitted value or the y hat, is just the sum of the grand mean plus the two main effects plus the interaction. And then finally I get the residual in a way exactly analogous to regression, where the residual is the difference between the data point y and the fitted value y hat, and in this case it turns out to be 4.6. Once I've done this decomposition, then my formulas for the sums of squares are simple. I just sum up the columns. Once I have the sums of squares, then I construct an analysis of variance table, which is really very similar to what you've done in regression. That is, I take my two factors and my interaction and my residuals, and I just put in the sums of squares from the corresponding columns right next to them. Each of these sums of squares has degrees of freedom. The degrees of freedom for any main effect is just the number of levels minus 1. The degrees of freedom for the interaction is the product. The degrees of freedom for the total is the number of observations minus 1. And the degrees of freedom for the residual is the difference. I'm going to test whether these factors matter by using mean squares. Mean squares are simply the sum of squares divided by the degrees of freedom. And then I take the ratio of the mean square for the two main effects and the interaction to the mean square for the residuals, the mean square error, in order to get a F statistic, which is basically asking, is the mean square for the factor, for example, temperature, big enough that it couldn't happen by chance? So my null hypothesis in each case is that the factor doesn't matter. My H0 here is that temperature does not matter. Okay, and similarly the H0 is pressure does not matter, and then the third null hypothesis H0 is that there's no interaction, and so on. And so since the null hypotheses are that the factor or the interaction is 0, we interpret the p-values as showing the evidence that those null hypotheses are contradicted or that the variable matters. So we can see in this particular case that the only thing that matters is the main effect for pressure. So this concludes my introduction for you to two-way analysis of variance based on the idea of decomposing each observation individually.